So we'll continue with reading 12 of the curriculum, and we'll now try to look at some of the issues in regression analysis. So we'll start by understanding the broad categories and what are the major issues. Understand in detail the effects, detection, and the process of correcting for heteroskedasticity, serial correlation, and multicollinearity. We'll see how the model or the regression equation can be misspecified, what do we do about qualitative dependent variables, and finally summarize so that we remember each of the concepts against one another. Now, the issues in regression primarily come from the assumptions that we have made in the regression. So please recall, the assumptions were first that a linear relationship exists between the dependent and the independent variable. If a linear relationship does not exist, then linear regression cannot be done. We need to either transform the variables or we need to find some other method altogether. The independent variables are not random, so they should not come from a stochastic or a regression type analysis themselves. There is no exact linear relationship between any two or more independent variables. So in multiple regression, this problem is called multicollinearity. We will study this in more detail in the coming slides. The expected value of the error terms is assumed to be 0. The variance of the error terms is assumed to be constant for all observations. If it is not constant, then the condition is termed as heteroskedasticity. We will also look at heteroskedasticity in more details in the coming slides. The error term for one observation is assumed to be not correlated with that of any other observation, or there is no autocorrelation or serial correlation. And finally, the error term is assumed to be normally distributed. So a few of these violations we'll study in detail, and we'll see what happens because of these violations and how can we correct for them. So heteroskedasticity is the condition when the variance of the residuals is simply the error term or the unexplained error, that is the actual value of the dependent variable minus the predicted value. So when the variance of these error terms is not constant across all observations, the situation is termed as heteroskedasticity. Unconditional heteroskedasticity is when the variance is not constant, however, it is not related to the level of independent variables also. So the variance is not dependent on the independent variables. This kind of heteroskedasticity creates no major problems with the regression coefficients and with the regression analysis. The more problematic aspect is that of conditional heteroskedasticity, which is the heteroskedasticity that is related to the level of the independent variables. If conditional heteroskedasticity is present, it may create significant problems in the inferences and the hypothesis testing that we do for our coefficients. So conditional heteroskedasticity would look something like this. So we see that the errors or the residuals are lower when the level of the independent variable is lesser, and the variance of the residuals or of the error terms tends to be higher or tends to go higher when the level of the independent variables goes up. So variance is not constant, it's increasing, and variance is dependent on the level of the independent variable. Hence, the situation will be termed as conditional heteroskedasticity. Now, what happens if conditional heteroskedasticity is present, or what are the associated problems? The problem is that the standard errors of the regression coefficients become unreliable estimates. So the coefficients themselves are not affected, or they are still reliably or properly estimated. However, the standard errors that go into the hypothesis testing of these coefficients become unreliable estimates. So what will happen if the standard error is overestimated, or if it is too high? Then when I do the t-test, which is equal to the coefficient divided by the standard error, this t statistic will come out to be too low. If it is too low, I may fail to reject. If I fail to reject an incorrect hypothesis, that may cause a type 2 error. So I may be making too many type 2 errors if the standard error is too high. If the standard errors are too small, it will be vice versa. Then the coefficient again remains unchanged, but the standard error is too low, hence the t statistic would be too high, and hence we would be rejecting the null hypothesis in a lot of cases even when it is true, or committing a type 1 error. So there is a possibility of too many type 1 errors or too many type 2 errors. Even the F test tends to be unreliable if conditional heteroskedasticity is present. So how do we detect conditional heteroskedasticity? One way is to simply look at the residual plot. Compute the error terms and plot them against the independent variable. So we saw in the previous equation the error terms were positive and negative, but they were smaller during the initial phase or when the independent variable was small. As the independent variable went up, the error terms also went up. So the y-axis now is the residuals or the error terms, and the x-axis is the independent variable. If the residual plot looks something like this, then you may want to worry about the problem of conditional heteroskedasticity. A more popular and scientific way of confirming heteroskedasticity is called the Bruce-Pagan test. So heteroskedasticity is present when the residuals are correlated with the independent variable. So if we perform a regression of the squared residuals with the independent variables, that is, as the dependent variables we have the squared error terms, so the error term for the first value, the error term for the second value, the error term for the third value, and for the independent variable I have the regular independent variable. If I perform this regression and the correlation comes out to be very high, then can I conclude that the error terms are related with the independent variable? So perform a second regression wherein the dependent variable is the squared residuals or the squared error terms, and the independent variable is your regular independent variable. Compute the R square or the coefficient of determination from that regression. This distribution is a chi-square distribution, and this test is a chi-square test, and the test statistic is calculated as n multiplied by the R square of this regression that has k degrees of freedom, where k is the number of independent variables. The null hypothesis in most of these tests will be that there is no problem. So the null hypothesis for the Bruce-Pagan test is there is no conditional heteroskedasticity. If this correlation, however, is too strong, then this value will be too high, and I will be able to reject this null and conclude that there is a problem with conditional heteroskedasticity. So this R square is from the second regression, n is the number of observations, and k is the number of independent variables. So let's do an example and understand. The residual plot of a stock's returns over time shows evidence of heteroskedasticity. When you regress the squared residuals from the original regression on the independent variable, that is the Dow Jones Industrial Average, the R square from that regression comes out to be 6%. Use the Bruce-Pagan test to determine whether heteroskedasticity is present at the 5% significance level. The question additionally mentions that 4 years of quarterly data is used. So if you are doing the Bruce-Pagan test, then our null hypothesis is that there is no conditional heteroskedasticity. The test statistic is calculated as n will be 4 into 4, 16 into the R square, that is 0.06. That comes out to be 0.96. The critical value for the chi-square test at a 5% level of significance with the given degrees of freedom comes out to be about 3.8, as 0.96 is less than 3.8. Hence, we cannot reject the null that there is no conditional heteroskedasticity. That is, the R square or this correlation is coming out to be too low for us to reject the null at a 95% confidence that there is no conditional heteroskedasticity, or to conclude that there is a problem with heteroskedasticity. If we conclude that we have a problem with heteroskedasticity, then the curriculum advises us to use white corrected standard errors, also called robust standard errors. Please recall, what was the problem with heteroskedasticity? That these standard errors are unreliable. So if we use the white corrected method and the white corrected standard errors, we will be taking care of that unreliability, and these revised values will give us the correct hypothesis test. We can also use another method called generalized least squares that is not as popular, that attempts to eliminate heteroskedasticity by modifying the original equation. So just know that there is one more method also available, but you don't need to know the details of that. Remember, normally if conditional heteroskedasticity is present, use white corrected standard errors. So we see a regression of stock returns on inflation rates, and we find out that using the Bruce-Pagan test, heteroskedasticity or conditional heteroskedasticity is present. The white corrected standard error for the coefficient on inflation is estimated to be 0.25. So instead of 0.2, the number that we should use is 0.25. The critical two-tail 5% p-value for the requisite degrees of freedom is 2.1. The critical value is also given. Is inflation statistically significant at the 5% level? If we do the original analysis, then the null that inflation is equal to 0 will have a t-statistic given by 0.5 upon 0.2, that is 2.5. So 2.5 is greater than 2.1, hence we would reject the null and conclude that inflation actually is statistically significant. However, if we use the white corrected standard errors, that is, we use the number of 0.25, then the t-statistic comes out to be 0.5 upon 0.25, that is 2 units. 2 is less than the critical value of 2.1, hence now we cannot reject the null, and we conclude that the inflation is not statistically different from 0 at the 95% level of significance. So we were incorrectly earlier rejecting a true null hypothesis, or we were earlier, because of the wrong standard error, committing a type 1 error. The next problem that we'll discuss in detail is called serial correlation. Serial correlation, also known as autocorrelation, refers to the situation where residual terms are correlated with one another. In positive serial correlation, we find that a positive error is followed by a positive error, or a negative error is followed by a negative error. In negative serial correlation, a positive error is seen to be followed by a negative error, and a negative error is seen to be followed by a positive error. So what is the effect of serial correlation on the regression analysis? Again, if positive serial correlation is present, and the curriculum discusses positive serial correlation in more detail, then we see that standard errors are underestimated or too small. That is, when I do the t-test, the coefficient upon the standard error, the t-value or the t-statistic is too high. That is, we will be rejecting our null too often or committing a type 1 error too often. Once again, the coefficient themselves are not affected, or the B1, B0 calculations are unchanged. The f-test also tends to be unreliable, as in the case of heteroskedasticity, as the mean squared error is underestimated. So remember, the f-test is given as mean squared regression upon the mean squared error. If mean squared error is too low, then again the F test will be too high and we will be rejecting this null more often than it should be, or we'll again be committing a type 1 error. So again, the coefficients are unchanged, but the F test is unreliable and the standard errors are too small, making us commit type 1 errors for positive serial correlation. How do we detect serial correlation? We can again look at the residual plot. So plot the residuals on the y-axis. If we see that residuals for subsequent values have a shape as shown, that is the positive values are followed by positive values, or the negative values are followed by negative values for the first part, then this looks like an issue of positive serial correlation amongst the error terms. If the error terms look something like this, that is a positive error is followed by a negative error followed by a positive error, then we'll say that it looks like a problem of negative serial correlation. Again, a more popular and a more mathematical method to check for serial correlation is called the Durbin-Watson statistic. So what are we now trying to check? We're trying to check if the error term in one period is correlated with the error term of the previous period. So we now do a regression with the error term for this period as the dependent variable and the error term of the previous period as the independent variable. And if this error, or rather, if this regression has a very high coefficient of determination or has a very high good fit, then can we conclude that the error term of the previous period is dependent on the error term of this period? So the Durbin-Watson statistic can be calculated as the summation t equal to 2 to t, the error term of this period minus the error term of the previous period squared upon the summation of the error terms for all periods squared. When the sample size is large, this calculation actually simplifies to simply 2 into 1 minus r, where r is the correlation coefficient between these two series. Now please tell me, if there is a very high positive serial correlation, that is r will be close to 1, or the Durbin-Watson statistic in that case will be close to 0. If there is a very high negative correlation between the two series, then the correlation coefficient will be close to -1 and the Durbin-Watson statistic would be close to 4. So for the Durbin-Watson statistic, any value close to 0 would indicate positive correlation. A value close to 4 would indicate negative correlation, where r is the correlation coefficient between the residuals from one period and those from the previous period. So I'm regressing this period's residuals with the previous period's residuals. So remember, the Durbin-Watson statistic would give us two critical values. So there will be a d lower and a d upper. If our calculated statistic is in between 0 to d lower, that is, it is too close to 0, then we'll reject the null hypothesis, which is that there is no serial correlation. Just like the null hypothesis earlier was, there is no conditional heteroskedasticity. So if it is too close to 0, then we conclude that there is a problem of positive serial correlation. If it is too close to 4, that is, it is between 4 minus dl and 4, then we conclude there is a problem of negative serial correlation. If it is in between dl and du, then Durbin-Watson test is inconclusive. We should take help of some other tests. If it is between 4 minus du and 4 minus d lower, then again the test is inconclusive. If the Durbin-Watson statistic is near about 2, if there is no serial correlation, this number would be close to 2, that is, it is in between du and 4 minus du, then we do not reject the null hypothesis and we conclude that there is no serious problem of serial correlation. So suppose you have a regression output which includes 4 independent variables that provide you with a Durbin-Watson statistic of 1.12. Also suppose that the sample size is 30. At a 5% significance level, determine if the error terms are serially correlated. So for the 5% level of significance and a sample size of 30, D lower comes out to be 1.31 and D upper, that is the critical value, is 1.72. So the Durbin-Watson statistic, that is 2 into 1 minus R, is calculated and given to be 1.12. So what will our conclusion be? So D lower is 1.31, D upper is 1.72. Similarly, I can calculate 4 minus D upper, 4 minus D lower, and 4. But I see that the Durbin-Watson statistic of 1.12 is lesser than D lower, that is in between 0 and D lower. Hence, I conclude that there is a problem of positive serial correlation. That is, I reject the null hypothesis that there is no serial correlation. So for correcting serial correlation, just like in the case of heteroskedasticity, we used white corrected standard errors. In the case of serial correlation, we'll use Hansen-White standard errors. Or these are also called serial correlation consistent standard errors. Please note that Hansen method also corrects for conditional heteroskedasticity. So if you see in the question, both serial correlation as well as heteroskedasticity is present, then you should use the Hansen corrected standard errors. Another method not very popular is again to improve the specification of the model by explicitly incorporating the time series nature of the data, that is, include a seasonal term, as we will study in the next review on time series analysis. So for now, just remember that use Hansen-White standard errors if you see a problem of serial correlation. The next issue that we'll try to resolve in detail is that of multicollinearity. So multicollinearity is a situation when two or more independent variables are highly correlated with one another. So the effect of multicollinearity is that the standard errors tends to be overestimated. If the standard error is overestimated, then the test statistic would be too low or underestimated. If it is too low, then I will fail to reject, and I'll often fail to reject even incorrect null hypothesis, causing too many type 2 errors. The estimate coefficients again are not affected or are unchanged like in the other two cases. And there is a greater probability that we'll incorrectly conclude that a variable is not statistically significant. That is a type 2 error. How do you detect? Very interesting test. So if there is multicollinearity, what you will see is that the individual t-tests indicate that none of the coefficient is significantly different than 0. So all individual coefficients tend to be insignificant. However, the model as a whole is statistically significant. That is, the F test is statistically significant, and we will see that even the R square or the fit of the model is quite good. So we see that the model's explanatory power as a whole is quite okay. However, all the individual variables are tending to be insignificant. What probably is happening is that we have included some or more variables that are highly correlated with one another. And that is why the individual coefficients are tending to not be very effective. However, as a whole, the model is very effective. If there is only two independent variables, then you will also see that the correlation amongst the two independent variables will be quite high. So just remember, if the correlation amongst independent variables is high, then there is a possibility of multicollinearity. But low correlation amongst independent variables does not necessarily mean multicollinearity is not present. So you will have to do the t-tests and compare it with the f-test. So let's see, in this situation, do we think multicollinearity is present? Wyeth runs a regression of stock returns on average price to sales, average price to earnings, and average market capitalization with the following results. Determine whether or not multicollinearity is a problem in this regression. So if we see the individual coefficients, then at a 5% level of significance, we cannot reject this null as it requires 10%. We cannot reject this null, nor can we reject the third null. So all the individual coefficients are not significantly different from 0, as we have been unable to reject the null that each of them is equal to 0. But if we see the utility of the model as a whole as regards the f-test, then we see that we can reject this null because it requires a very low level of significance. At 5% we can definitely reject this null, and even the r-square is quite high. So the model as a whole is explaining the dependent variable quite well. However, each of the individual coefficients is insignificant. This indicates a potential problem with multicollinearity, that is, you possibly have two or more variables that are highly correlated with one another, and hence the situation is happening. The price to sales and price to earnings look like they are highly correlated, and they should not be put together in the regression model. So how do we correct for multicollinearity? The method is simple. Omit one or more of the correlated variables. So if two variables are highly correlated, then basically you don't need both of them. Just putting one of them in the regression will suffice. However, this is easier said than done. You will have to one by one remove the variables and then do the testing again until you've eliminated the problem of multicollinearity. So please pause the video at this point and fill in the table for practice and revision. And please verify your answers. Another problem of regression is that the model can at times be misspecified. So there are various types of model misspecification. The first is that the functional form itself can be misspecified. For example, you missed out on an important variable. So we were trying to determine the price to earnings ratio of a stock, and we thought it was dependent on the dividend payout ratio, the growth, the book value, and we see that it's actually also dependent on the market cap. But since we've missed out on the market cap, we are incorrectly specifying the model. So we include a term for the market cap. However, the P by E is not directly linked to the market cap, or it is not linearly related to the market cap. It is linearly related to the log of the market cap. So the form is still misspecified as the variable should have been transformed. The third specification is the correct specification, where we have included the variable and we have transformed it so that it is linearly related to the dependent variable. The data can also sometimes be improperly pooled. So if data from two statistically and economically different time periods is being pooled together to estimate one regression equation, then that is also incorrect. That is, India before 1991 and after 1991 was practically two different countries from all economic perspectives, because it was a liberalized economy after 1991 and it was a closed economy until 1991. So if we are doing a regression for GDP growth and we are pulling in last 50 years of data, then that is not the right thing to do, or that will be a problem of improperly pooled data, because the economic relationships have changed. We should estimate two regressions, one for data between 1991 and 1970 and another regression for data between 1991 and 2013. So that's the problem when the functional form is misspecified. The explanatory variables can sometimes be correlated with the error terms, and this problem is especially visible in time series models. We'll study these models and these misspecifications more in the coming review. However, if we are using a lagged dependent variable as an independent variable, so in the prediction for y for this period, one of the coefficients is a lagged value of y from the previous period, then this will result in the problem of serial correlation. We will correct this in the next review when we study time series analysis. If a function of the dependent variable is used as an independent variable, for example, we are forecasting the returns on a stock and we are using the market cap as an independent variable. So if you use the beginning of period market cap, the relationship would have still been valid. If you use the end of period market cap to forecast the returns in the same period, then automatically the returns will be higher for higher market caps, because as the returns go up, the market cap goes up. So this would be an example of forecasting the past or using a function of the dependent variable. So market cap here is a function of the returns as an independent variable. So using variables measured at the end of the period to predict value measured during the period. Example, market cap at the end of the period as an independent variable and returns during the period as a dependent variable would create this problem. If independent variables are measured with error, for example, we are using actual inflation as a proxy for expected inflation. The model wanted changes in expected inflation in the example that we did. But because we are unable to collect data for expected inflation, we are using actual inflation. That will also cause an error. There can be other time series misspecifications also that we will study in the coming review that result in non-stationarity. So just keep this in mind. What stationarity means and what is non-stationarity we'll study with time series analysis. So what is the effect of model misspecification? The regression coefficients now themselves will be incorrect. So it's not just the standard errors. So there will be biased and inconsistent regression coefficients and hence unreliable hypothesis testing and inaccurate predictions. Now a small review towards the end of the reading tries to tell us as to what we should do if our dependent variables are not quantitative. That is, they are not numbers. However, there are some qualitative variables, for example, the quality of the company or the quality of the management or the chance of bankruptcy. So then how do we predict these qualitative aspects using regression? So the details of the models are not there. However, the first category is that of probit and legit models. So a probit model is based on the normal distribution, while a logit model is based on the logistic distribution. So we use the maximum likelihood methodology, details of which you do not have to know, to estimate the coefficients for the probit and the logit models. So these coefficients relate the independent variables to the likelihood of an event occurring. So we will have the price earnings ratio, the market cap, the competition in the industry as independent variables, and then we'll try to compute some likelihood or some probability of a qualitative result. For example, a merger happening or a bankruptcy or a default happening with these likelihood models. So that's one way of trying to quantify qualitative outcomes using regression models. A second category of models is called discriminant models, wherein we use a linear function similar to ordinary regression, which generates an overall score or ranking for a dependent variable. And then we can classify these rankings or these scores to be related to different outcomes. So if the score comes out to be between 0 to 5, then there is no possibility of bankruptcy. 5 to 8, there is some possibility of bankruptcy. 8 to 10, there is a high possibility of bankruptcy. Another way of trying to estimate qualitative outcomes with the help of linear regression type models. So nothing detailed is mentioned, just the brief introduction to these two types of models are given. Basically they want to specify that even qualitative or dependent variables may not always be numerical. Sometimes they can be qualitative outcomes also, and we may need to apply transformations. So just to summarize the readings that we have studied, we'll start and check if the model is correctly specified. If no, we will correct the model specification by transforming the variables, including any omitted variables, so on and so forth. So once the model is correctly specified, we'll do the t-test to test if the individual coefficients are significant and if the model is statistically significant. If not, then we'll have to change the model or again start with some other model. If yes, then we'll check for the problem of heteroskedasticity. If it is present, then we'll correct using the white standard errors. If it is not present, we'll correct or we'll check for the problem of serial correlation. If it is present, we'll use the Hansen-White methods or the Hansen corrected standard errors. Then we'll check for multicollinearity. If it is not present, we'll use the model. If it is present, then we'll drop one of the correlated variables and then use the model and perform our regression and interpret the results. So that was about the review on multiple regression and the issues with multiple regression. A slightly complicated topic, but interesting nonetheless, and make sure you practice a lot of questions so that you're able to master all the concepts and you're hands-on and you're comfortable with all the calculations. So thanks a lot, and see you next time.